Hello, good morning. I want to welcome all of you to the SWARDAM conference. I'm sorry that I'm not able to present this in real time, but I hope my recording is able to convey the message that I'm trying to convey. So I'm Venkatesh Mirwade. I'm a faculty in the Lyle School of Civil Engineering at Purdue University, and the title of my talk is Water Resources Management Using Data, Computational Modeling, and Cyber Infrastructure. The work that I'm going to present today is a combined effort by a lot of students, so I want to acknowledge them on this slide. Many of them have graduated, some of them are still ongoing. So given that the work that I'm presenting is done by all these great students I had opportunity to work with, it is not possible to present everything in 30 minutes. So what I plan to do is give you a flavor of the work that has been done and ongoing in my research group at Purdue University. This slide shows the hydrologic system. So when we try to manage water or plan for water in the future, we want to understand how our hydrologic system works. So on the left, you see the hydrologic system and the different processes that are part of the hydrologic system. So we have rainfall, evaporation, infiltration, percolation, groundwater flow, and so on. And on the right, we try to simulate these processes by using different models. And not all models represent the hydrologic system completely or holistically. So what you see on the right are different layers that we include in a particular model. So on top you see a channel flow. So if you are using a 1D HECRAS model or any other hydraulic model for river hydraulics or flood modeling, so that is what you include. Some of you may be using SWAT. So SWAT, HMS, they include the channel layer to some extent, and they include the surface part and the subsurface part, but they don't include the deep groundwater. And then there are some models that include all these layers. So depending on our problem and what we are trying to do, we may end up using a simple model or a complicated model. So to simulate hydrologic processes, we have access to different data sources. So on this slide, you see land use data, topography data, soil data, groundwater data, impervious cover, and on top of that, we have access to precipitation, temperature, and all these data sets. So what we are trying to do in our research group is we are trying to improve our understanding of hydrologic system through improved simulation of physical processes by using available data, computational tools, and cyber infrastructure. So what I plan to do in the next set of slides is to give you a flavor of some of the ongoing work that is going in our group. So what you see here is Ohio River Basin. So those of you who are not familiar with the geography of the United States, I'm showing you a map of the US, and this is where the Ohio River Basin is. So the total area of this basin is about 500,000 square kilometers. So what you see on this slide are land use in this basin from 1935 and 2015. So we have two snapshots, and you can see the land use has changed significantly between these two timestamps. So we see increased in impervious cover or urban land. We also see increased in forest area, and in some area we see both decrease and increase in agricultural land. So what we are trying to understand here is how the blue water green water dynamics has changed in this last 75 years by using a model called SWAT, and I know some of you are familiar with this model. So instead of going into all the details, what I'm presenting here are the results. So blue water is the water in rivers, aquifers, lakes, or reservoirs. So you can think of this as the fresh water that we use for domestic supply. and industrial use and irrigation. So you can see that there are areas where the blue water has increased, there are areas where the blue water availability has decreased, and then there are areas where there is no change. And if we look at the area that have been impacted and where the blue water has changed, you can correspond that to the change in precipitation, and in some sense we can relate that to the change in climate. So the climate change has impacted the blue water dynamics in the Ohio River Basin. And then let's see how the green water has changed. So green water is that water that is stored in the subsurface and it circulates within the water cycle through evapotranspiration. So again you can see the upper region we have increased groundwater. In the lower region also we have increased groundwater, and the middle region there is no significant change in green water availability. And this is driven by the land use change. So if you remember the land use map I showed you earlier, there is increased forestation in this part of the basin, and this part is driven by the dynamics of both land use and climate. So what we try to do here is to use historical data and computational tool to understand how the land use and climate has impacted the blue and green water availability in the Ohio River Basin. And the goal of this was to come up with a methodology that can be applied to similar basins within the US and around the world to see how the water availability has changed in the last 75 years that can help in making future planning and decisions. We spoke about the historical change in land use and climate. We tried to do similar study in the upper Mississippi River Basin. So again, those of you who are not familiar with the geography, this is where the Ohio River Basin was. So upper Mississippi River Basin. So again, it's a big basin similar to the Ohio River Basin. And what you see here are two maps. One is a land use scenario and the other one is the climate scenario. So the question again we tried to ask here was, how is the future land use and climate change? And when we talk of climate change, we have multiple scenarios. So how the combination of these scenarios and projected land use is going to impact the hydrology of this basin. And we focused on some urban areas which we think are the hot spots in this region. And what you see here is change in surface runoff and evapotranspiration. So surface runoff, you can again think of the freshwater availability. Evapotranspiration has to do with the change in land cover and vegetation. So depending on the scenario you have, you are going to have areas where we will see increased runoff, we will see areas where the runoff will decrease. Similarly, depending on the land use and climate, we will see areas where the evapotranspiration is going to increase, and in areas where the evapotranspiration is going to decrease. So you have multiple scenarios. The question then is, how do we evaluate or look at all this in holistic way? So what we did in this case is we came up with the ecosystem efficiency index, and the idea here is if the index is close to 1, then this area is going to be very inefficient in terms of water and energy efficiency. And as the ecosystem efficiency index is 0, then the area is going to be more efficient in terms of water and energy use. So the goal of this was to come up with a way where planners and decision makers can use this index to think about what kind of changes we want to make in our watershed, so we have an efficient system where the water and energy is being used very efficiently. So we talked about the change in land use and climate. The next question that we are going to ask is how some human impacts is affecting the water availability. So in this case, we are going to use an example of sand dams. So sand dams, these are small scale dams There are thousands of them in East Africa. The question that we are trying to answer here is how sand dams are affecting water availability in the region. And since there is not of field data collected to see how these dams are impacting, we don't even know whether it is possible to quantify this impact. This is a schematic of what a sand dam is. So these are low head small scale dams, sometimes a concrete structure or earthen dam that is built across a river. So here behind that, what happens is these rivers are sandy, so because of this obstruction the sand will get accumulated behind the dam and that will store water. And the idea of these dams is to store water so it can be used when there is no rainfall. This is how an actual sand dam looks when there is no water. So you can see it's filled with sand upstream, there is nothing downstream. And this is the picture of the same area after a rainfall event. So you can see there is water here which is stored within the sand, and you see some ponding. You can see that this dam is really not working efficiently because there is some seepage under the dam. So in order to quantify the impact of sand dams in this region, since there is no field data, we ended up using satellite data. So in this case, we used GRACE data that tells us how the groundwater is changing. We used data from this modeling system called FLDAS, and then we used Moody's data to quantify the change in vegetation. So what we did was we created a simple water balance model. So the idea here is we have rainfall information. If you subtract the runoff and evapotranspiration, which we will get from FL-, what we get is how much water is getting into the ground. And then can we relate that groundwater change to what we observe from the GRACE data. So what you see in these plots, there is sand dam counties, then there is buffer area. So if the sand dams are impacting an area, that area should influence not just where the sand dam is, but the surrounding area also. So what you see in this is that the dynamics that this equation that you see on top is creating is matching with what the dynamics that we get from GRACE. The question then is the amount relating to what we see in the GRACE data and the model. So the answer is yes, we do see that sand dams are having an impact on water storage based on the water balance model that we create, but we are not able to see the same amount of change from GRACE data. And the conclusion that we have from this is that the sand dam influence water storage in area that is too small to be captured by the GRACE satellite because of the resolution of that data. So instead, what we try to do is let's look at the change in vegetation. So what we see there is sand dams have a statistical significant and positive impact on vegetation covers, and this map shows what is observed in terms of vegetation change and what we predicted from the model, and they do match. So we are able to say that the model predicts trends in vegetation quite well, but sometimes it under predicts the extreme high and over predicts the extreme low. But the important point here is to remember that the model upholds our hypothesis that sand dams positively impact vegetation. So we were not able to show the change in groundwater by using GRACE, but we were able to show the change in vegetation due to sand dams. And then there are studies that have shown that the change in vegetation is related to change in groundwater availability. So we were able to show indirectly the impact of sand dams on water availability in this region by using satellite data. In this study, what we tried to do is how can we use data and computational tool to improve our stream flow prediction at regional scale. So there are a lot of ongoing efforts to create flood information at finer scale. So what you see on this slide are stream gauges within the Ohio River Basin. So we have about 700 stations, and if you think about that, we have about one station per 700 kilometers square. So the data is extremely sparse, as you see on the right. So what we are trying to do is how can we use information at these gauging stations that you see in red to come up with stream flow prediction and flood inundation in all the other reaches that we have here. So the question is, how do we go from 700 hydrographs, this is where we have gauges, to 100,000 hydrographs? So in this case, again, we are using SWAT model to do that. Now, in traditional SWAT modeling, what we do is we do rainfall runoff modeling. We drive the model using rainfall. We compare the output with available stream flow or runoff data at those gauges. And what we have seen by doing that kind of rainfall runoff modeling, it may work in small watersheds and small basins, but as we look into larger and larger basin, just calibrating or looking at rainfall runoff does not help. So when we do rainfall runoff modeling, we try to look at the water balance. So what we have found, when you want to do this over larger areas, over larger subbasins, you just don't have to look at the water balance, we also need to look at the energy balance. So what we tried to do in this case was, instead of just calibrating the model using stream flow or runoff, we brought in leaf area index, we brought in potential evapotranspiration, and we brought in soil moisture. So that way we are able to not just relate one flux, we are able to calibrate and relate multiple fluxes and create a model that has more physical meaning. And by doing that, you can see from these two maps here, this has much higher uncertainty in our prediction, and this has much lower uncertainty in our prediction. And on the right here, you see the uncertainty band. The band got narrowed when we incorporated these other fluxes into the model from observation. So many of these models, they estimate these fluxes, but we do not have a way to compare whether these fluxes correspond to what is happening in nature, and satellite data gives us a mean to do that. So if we have improved stream flow prediction, the question then is, can we then improve our flood inundation maps and flood inundation extent? To do that, we extended that SWAT study by combining with LISFLOOD-FP. This is a two-dimensional flood inundation model. Since this is a two-dimensional model, it does require a lot of computational resources. So we ran that on a HPC system, and this is what you get. So again, you can see that we are able to create flood inundation at 100,000 reaches within this basin, not just at 700 location. And by looking at the F and C stat, so these are some of the indices that we use to compare inundation extent with observed data. The F and C stat of close to 7 and 0.8, that's a very good when we think of uncertainty associated with simulating this. So what we get from SWAT and LISFLOOD is just one realization. So the idea here is, if we have multiple estimates, how can we come up with an ensemble, and that will give us not just one flood inundation map, it will give us a probabilistic flood inundation map. So instead of using one input, we use multiple inputs. Instead of using one model, we use multiple models, and then we end up with probabilistic stream flow estimates that you see here. So in this case, we are using only two models, but the idea here is that if we have more observations, more models, we should come up with a probabilistic estimate of stream flow, and then that probabilistic estimate will give us probabilistic flood inundation, where we have more confidence on what we are presenting. So what you see again here on the left is a deterministic inundation map, which has F and C stat of 0.65 and 0.75, and on the right you see a probabilistic flood inundation map, and that has a f-stat of 0.7 and 0.95. So much better than what you would get from deterministic estimate. So what we are trying to do is, instead of creating deterministic flood inundation map, we should be producing probabilistic flood inundation map, because our estimates are not accurate, so we should be doing probabilistic flood inundation mapping. So until now, what I showed you are studies that are done using like more traditional 1D hydraulic model, a simple SWAT or HMS model. But as we go into more complex hydrologic system, especially in urban areas, those simple tools really don't work. So we need an integrated approach, and that is what we have been trying to do in the recent years using a model called ICPR. So this is a totally integrated model that does surface, subsurface, deep groundwater, urban infrastructure, you name it, you can simulate that. And since this is a complicated integrated model, it does require a lot of computational resources. So what we are doing is, instead of creating a complex integrated model for large areas, we use complexity where we need it, and we use simplicity where we don't need detailed information. And that is what you see here, a detailed mesh where we need detailed information, and a sub-basin based approach where we don't need detailed estimate. And it's hybrid not just in terms of representing the processes, it's hybrid in also simulating these processes at different scales. So this is again a hybrid watershed where you have flood inundation, detailed flood inundation along river, and detailed inundation in an urban area. And these are just some results. So again, where you want detailed flood inundation, you have that, and this is how the computational mesh looks. And if I run an animation here, so this is what it will give for the detailed integrated mesh. But if you are just interested in inundation, you can still create that inundation map. This is again, you have detailed flood inundation along the river where you need that information along the river. If you have an urban area, you get street level flooding information, not just what is happening at the river. This is just an animation of how the inundation is changing in space and time by using this hybrid approach. We did this for Hurricane Harvey. So Houston is a very complex urban environment. The question was, will this hybrid approach work in that complex environment, and is it able to give accurate information for an extreme event such as Harvey? So in case of Harvey, we got 40 inches of rainfall in only few days. So the question was, if we have this system, will it work? And will it give accurate information? And the answer was yes. So what I'm showing you here is the flood dynamics during Harvey in the Houston area. So this is just showing you how the water dynamics is changing on the surface. And then if we compare the results from this with observations from these plots, you can see that our estimates were very accurate, with the R square of 0.96 and more than 0.8 in most of the times. And then we also compared, so we don't just want to estimate accurate stream flow, we want to estimate accurate inundation depth. We compared our depth with what was measured by some agencies, and the histogram here shows that our predictions were accurate. So this 0 means our prediction matched exactly with what was observed with inundation. So overall, about 80% of the inundation depths that we compared from our model with observations were in less than 1 meter range. This just shows the inundation with observed images. So So wherever our model says will get inundated, that was inundated during Hurricane Harvey. So this is a complex model. It does require a lot of computational resources. So we are trying to reduce the computational demand by using this hybrid approach, and then can we use this over a large area. So what you see here is the same model running for Wabash Basin. So Wabash covers almost the state of Indiana. So this is 85,000 square kilometers square, and you can see we are able to run and get flood inundation at the street level by using this model. So while I showed you complex modeling giving flood inundation, but if you don't have access to these resources, then you can look for non-conventional ways of coming up with these flood inundation maps. So what I'm showing on these slides are two maps. One map is created by using computational tools, complicated hydrologic and hydraulic modeling, and the other map is created by just using soil data by an undergraduate student. If I ask you to tell the difference between these two maps, many of you may say there is not much difference, and it is true. So this is soil-based map, and this is a FEMA. So FEMA stands for Federal Emergency Management. FIRM is FEMA insurance rate maps. So the green map cost hundreds of millions of dollars, and the red map is relatively free. So while we are doing all this complex, complicated hydrologic and hydraulic modeling, we are also using data-driven approaches to come up with these results. So we extended that for the whole US, and you can see we have a flood plain map for the entire US by just using soil data. When we talk about data-driven approaches, so we are also looking at how we can use machine learning to come up with fast prediction of stream flow. So this is still ongoing work. So you can see that at HUC4 level, so our prediction accuracy changes depending on our spatial scale. So we are trying to look at what spatial scale we can get accurate prediction. So you can see we can get a Nash Sutcliffe efficiency of 0.8 at this HUC4 level. So if we can get that kind of accuracy, can we predict stream flow much faster for millions of reaches in the US and hopefully in other areas if we have that framework in place. I would like to spend just some time talking about the role of infrastructure in what we are doing. So we do a lot of modeling. So what we are trying to do is we make those models open and accessible and reproducible. So we have a system called SWATSHARE. People can share their models on SWATSHARE, and beyond sharing, we have tools to run those models and visualize model output. So this is one resource that we have. Once you have your model in SWATSHARE, you can actually make the results visible. So what we try to do is we use the SWAT model that we have created for Ohio River Basin and come up with a flood information system. So this is a SWAT model for Ohio River Basin. So if I click on any area, I can see what the hydrograph at that place looks like. And then if I click at any point on the hydrograph, I can see what the inundation looks like. We are using a lot of satellite data, so we have created tools so people can also access satellite data easily. So we are calling this platform as HYDROGLOBE. So one can download satellite data for a given region by using HYDROGLOBE tool. We are also working on a system called River Morphology Information System. So many times we are doing detailed hydrodynamic modeling for flood inundation, but most of the times the critical data set, which is the river bathymetry, river morphology data, is not available. So we are creating a system where people can publish and share river morphology data, and we are also working on tools to create synthetic river morphology and bathymetry data for use in river studies and flood inundation modeling studies. Finally, we are also working on an open knowledge network. So we do all this work. So the question is, can someone use this information to help them during extreme events? So you can think of this urban flooding open knowledge graph as a Google for flood information. So in this case, we have these different people, we call them personas. So buyer Bob is asking, can I buy a house in this neighborhood? So he should be able to use a platform such as this to find out whether his house is at risk. Similarly, a floodplain manager can ask what areas in my city are at risk, or any other person may ask, if there is a flooding, can I go to office or drive safely to office tomorrow? So these are the kind of questions that people can answer by exploiting the results from these complicated models. So this is again a new ongoing project, and this is my last slide. So in summary, I would like to say that new multi-scale geospatial data are providing new opportunities to understand and simulate hydrologic system. High performance computing and big data solutions are providing new opportunities to improve water resources management. Selecting an optimal approach is dictated by the problem and data availability, and cyber infrastructure is providing new avenues to access data, models, and their integration, thus providing solution to existing research problem and providing new research opportunities. And what I try to do in this talk is to give you a flavor of what I'm saying on this slide. And with that, I would like to end my talk. And as I mentioned, I am not able to give this talk in real time, so this is a recorded video, but please feel free to reach to me for any questions, or if you need any additional information about the work that I presented. So this is my contact information. You can email me, you can message me, or you can follow me on Twitter. So with that, I again want to thank the conference committee for giving me this opportunity, and I look forward to hearing from some of you. Thank you very much.